Today we want to talk about double integrals. We want to remember that integration is multiplication, but one of the factors is continuously variable. And that means that integration is just addition. The game that we're going to play is the same game that we played back in Calc 2. Evaluate f of x times dx for all the values from a to b. Now we're just upgrading that. Evaluate f of x and y times dA for all the values or all the points in some region. So what the double integral is going to look like is we're going to integrate over some region a function dA. Just like we thought of our definite integrals as the area under a curve and above an interval, we're going to think of this as the volume under the surface f of xy and above the region R in the xy plane. So we're going to think of this as the volume under the surface and above the region R. What we need to do is evaluate that f of xy times dA at all the points in the region. So the integral over R part, that's telling us the values that we need to plug into f of xy times dA. So the integral part this is telling us what points xy we're going to be plugging into f of xy dA. F of xy, we're going to, if we think of it as a volume, f of xy will be the height and dA will be the area. So dA is like the area. And f of xy will be the height. And so we're making the calculation height times area over all the points xy that is described in the integral over R. At the top of the class, I promised you double integrals today. You're like, oh, what is this? This looks like one integral. It's a double integral because we're integrating over the region R. So we're going to split this double integral over R into two integrals. One where we describe the x's and the other where we describe the y's. And we're going to split the dA into x's and y's. There's going to be a dx and a dy. So if the dx is the first thing listed as the dA, then our first integral will be x. And then the other one will be dy. And that would mean the outer integral will be the y integral. Notice that this double integral, now that it's split into x's and y's, Now we have the two integrals, one for the x and one for the y. That's the double in double integrals. And we also split up the dA into a dx times dy. The other way we could write this is the other order. We could split the dA as dy times dx. If we write dy first, then that inner integral is going to have to be y. And then with dx second, the outer integral will be the x integral. But if we want to describe a region, all we have to do is say it's between these x values and these y values. That's what we're trying to do. We just want to make sure that we match up the correct order. That outside integral should be the outside dx or dy. The inside integral is the first dx or dy that's listed. So we're going to talk about inner integrals and outer integrals, just to make things easy. But we're describing the region. It's between these x values, oh, that's the other way around, between these x values and these y values, or between these y values and these x values. The point is, we have to tell the integral where to calculate f at xy dA. So here's how we're going to describe that region. So this double integral part is describing the region by listing what x is between and what y is between. So that's how we're going to play the double integral game. This was a lot easier in single variable calculus because we're just choosing a bunch of x values to plug into f at x times dx. All we were doing was plugging in values from an integral. So we could just say start at A and end at B. But now we're describing regions. So let's talk about how we can describe these regions. Let's talk about the rules. The rules go like this. This outer integral, the last one that gets computed, that integral has to be constants. So the last integral, the way I usually phrase this is that the last integral must be constants. So the way I usually phrase this is I say that the last integral only gets constants. So from A to B, we only get to use constants on the last integral. The earlier integrals get to use functions of upcoming variables. That's the way I usually phrase it. The earlier integrals get to use functions of upcoming variables. So in this one that's labeled, if dy is first, that means this first integral can use functions of x. So y could start off with some function of x and go up to g2 of x, and I didn't give myself enough space. I can put functions of upcoming variables in the early integrals. But the last integral only gets to use constants. So if I have x as the last integral, I have to go between constants, x equals a to x equals b. If we look at the previous one, where x is the first integral and y is the last integral, the first integral can use functions of upcoming variables. So x can be integrated between two functions of y. So h1 of x, let's say, and of y. I just said y. And h2 of y. But in this setup, I get to use functions of y in the first integral. Then the last integral can only use constants. So y will have to go between constants. C to D, let's say. Now what we need to do is look at a region and describe it to a double integral. Then we have to look at a region and describe, look at a double integral and describe the region. So the connection that we're making is between a region and the double integral. And we have to be able to go back and forth between these two. If I give you a region, you have to describe the double integral. If I give you a double integral, you have to be able to describe the region. Once we have the double integral set up, we would have to presumably calculate the double integral. So let's describe some regions. Let's start off with a region that we're going to describe to a double integral. So let's describe a region to a double integral. Now, here's the great deal about these problems. There are two ways we could set them up. It's dx dy or dy dx. That means every one of these problems is actually two things for us to do. So that's exciting. Everybody loves a buy one, get one. Let's draw a region. And we're going to start with a nice simple region. Let's suppose that the region R is just a rectangle. And let's say the base of this rectangle, the x starts off at 0 and goes up to 5, and the y starts off at 0 and goes up to 3. We're going to describe the region by saying what's x between and what's y between. And this is the simplest case. X goes from 0 to 5, and y goes from 0 to 3. I just realized I wanted to do something different, but that's okay. So to describe this with a double integral, right now I'm not concerned about what the function is, so I'm just going to write f of xy. But I have to decide what order I'm going to write it. I'm just going to follow the order that I did up here, start with dx dy. So the first one, if I write dx dy, that means that first integral, I'm going to write what x is between. X starts at 0 and goes up to 5. So I just get to go x equals 0 to x equals 5. The last integral has to use constants, which is all that we want to use anyway. We start off at 0 and go up to 3. So y equals 0 to y equals 3. So here's a dx dy integral. Normally when we write integrals, we don't write x equals and y equals on our integrals, but we're new at this, so we're going to keep track. We know which corresponds to which, because if dx is listed first in the dA, then that first integral is an x integral. And with dy listed second, we know that this second one is the y integral. But we're new, so we're going to label it. Like when we were new in algebra, and we said 5x minus 4x, and sometimes we just wrote 1x. When we were learning about fractions, we had to do some fraction operations. We might have written 2 as 2 over 1. So there's all these understood pieces. This one eventually will be understood, but for now, we're going to label it. Especially because that's the point of the exercise. We can also write this as a dy dx integral. So if I write it as a dy dx integral, that means first we'll list the y values, and then we'll list the x values. That last integral has to use constants. That's okay. That's all I want to use in this one. Okay. Now we might want a way to check to see if this is going to work. If we integrate the function 1, that should give us the area of the region. Just like if we integrate the function 1 in a single variable, it will give us the length of the interval. The integral from a to b of 1 dx is going to be x evaluated from a to b. That's going to be b minus a, the length of the integral, or the interval. So integrating the function 1 should give us the area of the region. Integrating the function 1 oops. The integral of the function 1 dA will tell us the area of the region R. Just like integrating from a to b, the function 1 dx will give us the length of the interval from a to b. I mentioned this now so we could check that our integrals are going to give us the right value. And also because we're going to eventually go from double integrals to triple integrals in a move that is super predictable. And when we switch to triple integral, the integral over some solid W of 1 dV will tell us the volume of the solid W. How's everybody, okay? No one is going to be surprised by this when it shows up. Even if I try to deny it. Like when we're talking about Star Trek Into Darkness. They're like, oh, who's Benedict Cumberbatch playing? And they're like, oh, nobody. As if we didn't know. They're like, oh, no, 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 it's not what you think. And we're all like, it's exactly what we think. And so they go, no, 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 it's not what you think. Then the movie comes out. You said, see, it's exactly what we thought. Just lean into it because you're leaning into it anyway. Because that big reveal doesn't have the same impact in these 2 Star Trek films that came out. You know what I'm talking about? I don't know if you've seen this. I don't know if you're a Star Trek fan. But it didn't work. Because we haven't been invested in this for years and years and years. You know what I mean? There's no history there. What made it good in the original was the personal history between Kirk and this other person. Anyway, that's all beside the point. I realize this might be classified as spoiler alert. There's a statute of limitations on that stuff. If you haven't seen it by now, you don't get to have this. You just have to be spoiled. Darth Vader is Luke's father. That's not a spoiler. That movie came out in 1981. If you haven't seen it by now, that's on you. You know, you can go, oh man, spoiler alert. Meanwhile, if you see a movie that has anything that might even be construed as a spoiler, you can't walk out and say, I don't want to spoil it for you. Because now you've just implied that there's something to be spoiled. So you don't have to tell me what the twist is. If you mention that there's a twist, you've already spoiled it. You know what I mean? So if they go, I'm not going to tell you the big twist. I go, well, fuck off. You just told me that there was a twist. And so now I'm going to be looking for one, and now I'm going to figure it out. So I have to find a way to enjoy movies when they're spoiled. You know what I mean? At least Marvel told you what was coming up. It's like, oh, Thanos has got some plans. It's like, well, we all know what Thanos' plan is. We read the in comics. So they don't try to say, oh, no, no, it's not going to be that. When it's exactly that. And I go, fuck it, let's just lean into it. You know what I mean? Anyway. So if you ever find yourself saying, I don't want to spoil it for you, you are spoiling it. Just say, now, I don't talk about movies that I've seen that other people haven't. Then when they get out of the movie, they're like, well, there was no spoiler in that. They're like, well, yeah. And it's a good thing I just didn't tell you that there wasn't any spoiler because, you know, people are really sensitive about the spoilers out there. And I think the real solution is not giving a F about the spoilers. You know what I mean? Don't make a whole movie just because you thought of a cool spoiler, a cool twist. You can't make a whole movie on that. And especially can't make a whole career out of it because then people start looking for it. You know what I mean? Anyway, let's integrate. So we had the integral from 0 to 5, and then the integral from 0 to 3 of 1 dy dx. Because we also have to be able to calculate these integrals. So let's be able to calculate these integrals. Now, the first integral that we run into, we're going to integrate 1 dy and then evaluate from 0 to 3. So the integral of 1 dy is y, and then we're going to evaluate from 0 to 3. We still have to integrate from 0 to 5 dx. And now we see that we're going to get the area, because if we integrate 3 dx, that's going to be 3 times the length from 0 to 5. Similarly, if we switched them, we integrated from 0 to 3, then from 0 to 5, dx dy, we will also get 15. Question? So this is a good way to check. If we can look at the area, know what the area, look at the region and know what the area is, that gives us a good way to check that our double integral is set up properly. This is an important thing to have when we're new to this double integral business. Let's look at another region. So I'm still going to have a 3 up here, and I'm still going to have a 5 down here. But now the region is going to be a triangle. I'm just going to connect the 3 down to the 5 with a line. And we want to do the same thing. Describe this region for a double integral. Actually, for 2 double integrals, a dx dy and a dy dx. Now, we're going to need to know what this line is. So I'm going to write the equation of a line. I'll start off at 3, and we'll decrease by 3, but it'll take 5 units times x, and this starts off at 0, so I'm going to just use minus 3/5 x. So we're going to describe this in two integrals. I'm going to start with the dy dx integral. Let's describe this as a dy dx integral. So this first one is going to be y equals to y equals, and then the second one dx will be x equals to x equals. Because we know that the last integral has to be constants, it's the most convenient one to start with. Look at the values of x for this integral. X goes from 0 to 5. The last integral has to be constants. The only ones that make sense, x equals 0 and x equals 5. So that's what we're going to lead with. Next, what we're going to do is say what y is between. So we're going to pick a typical x value, find the lowest y, and then the highest y. So for a typical x value, for a typical value of x, it looks like the lowest y value is y equals 0. And the highest y value is going to be at the function. So for a typical value of x, write down what y is between. And that tells us how to set up the integral. Y should go from 0 to 3 minus 3/5 x. If we want to check that this will work out, we can integrate the function 1 to see if it gives us the area of this triangle. That's what should happen. So if we have the function 1, when we integrate dy, we evaluate y from 0 to 3 minus 3/5 x. That's just going to give us 3 minus 3/5 x. And if we integrate from 0 to 5, the function 3 minus 3/5 x, that's going to give us the area under 3 minus 3/5 x and above the interval from 0 to 5, which we know will give us, which we just said will give us the area. So integrating the function 1 will work out in this case. But that's not the only integral that we have available. We can also set this up as a dx dy integral. So if I write a dx first, that means this first one is going to be x, and the last one is going to be y. So in this case, I have dy as my last integral, and that has to only involve constants. So we just write down what's y between, what two constants are y between. Y starts off at 0 and goes up to 3. Now we need to pick a typical y value and see what x is between. So here's a typical y value. Now we just need to see what x values is this between. Looks like it starts off at x equals 0. And for the other one, all we have to do is take the equation y equals 3 minus 3/5 x and turn it around. So if y is equal to 3/5 x, y is equal to 3 minus 3/5 x, then y minus 3 is equal to minus 3/5 x. Now multiply by negative 5/3. And that'll give me x. Notice that negative 5/3 times the negative 3 tells us that x starts off at 5. And decreases by 5 when y increases by 3. And here's how we'll describe the region in the dx dy. X will start off at 0 and go up to 5 minus 5/3 y. Like before, we can integrate f of x y equals 1 to find out that these two double integrals will give us the area of this triangle. So integrate the function f of x y equals 1 to confirm the area of the region. Since it's a triangle, no problem. We're just trying to tell the integral what values of x to plug in, then what values of y to plug in. Questions? Let's take a look at a slight variation of this. I'm still going to have a triangle for the region, and I'm still going to use 3 and 5. I've never been accused of being all that creative when it comes to examples. So I figure, why start now? I still want the line starting off at 3 and going down to 5, or down to 0 when x equals 5. I still want this. But I don't want the region below this line. I want the region above. I want the top half of this rectangle. And I want to describe this region, this top rectangle, to a double integral. And I want to do it in 2 different ways, a dy dx and a dx dy. Now, this line is still the line y equals 3 minus 3/5 x. And I'm probably going to still need that line to be written as x equals 5 minus 5/3 y. But it's going to show up differently in the double integral. So let's do the double integral dy dx. Now I know that that last integral can only involve constants. So we just have to look at what values of x are the constants. Then x still goes from 0 to 5. So now we're going to pick a typical x value and see what values of y we are between. So here's a typical x value, but we don't have the region until we get to this line. And this above part is where the region is. So the lower bound is going to be the line, and the upper bound will be the constant 3. So start off at the line and go up to 3. Which region we grab is defined by the problem. When we evaluate the function 1, we're going to get the same values that we found in the previous example. And the bottom triangle is 7.5, the top triangle is also 7.5. But what we need to be concerned about is the values that we're plugging into f of x, y. The value of the function might be very different from the bottom half of the triangle to the top half of the triangle. Or from the bottom triangle to the top triangle. We need to set up the other integral. So if we integrate f at xy dx dy, then x is going to go first, or x is going to have to be allowed to use functions of y, but the y's have to be constant. So the constant ones, the last integral is always the easiest one to figure out. What's y between? Y goes from the lowest y value is down here at 0. And the highest y value is up at 3. The lowest y value that describes that region is 0. The highest y value is 3. We're not worried about that big line cutting through the middle. Down where it says x equals 5, that's where y is equal to 0. So that's where the y's start. Now we're going to pick a typical y value and see what x values we're between. So here's a typical y value. And we start at the line. So we're going to start our x's at the line, which is still 5 minus 5/3 y. And the x's stop when we get to 5. Any questions? Now what we have to do is look at other configurations, right? What if I made the line go from 0, 0 up to 5, 3? Then what if instead of a line, we had some other kind of curve that we described with the function? So I could connect the line, instead of going with a line from 3, 0, 3 down to 5, 0, I could make that a parabola bent down. Questions? Comments? Snide remarks. All right. We'll look at more double integrals tomorrow. That's going to do it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.